I hopefully, oh, by the way, hopefully you all had a lot of fun during that hackathon. I know it can be really stressful, but you know, it's supposed to be fun. So let me just get everything set up for you all, and this should work. Why is the file? The screen recording. Okay. Is it? Whoops. Okay. File, new screen recording. Okay. Can you all hear me? Yeah. Okay. You can all see me, and now you can see my screen. So what we're going to be going over today is, in my opinion, the most complex topic of hacking. It is not easy. How many of you did the pre-work for buffer overflows and watched some of the videos and read the book? If you did, you definitely will find that very beneficial going into today. Here's what I say to you all. How many of you are planning on, who have your OSCP scheduled? How many of you have your OSCP scheduled? Should be almost all of you, right? Having it scheduled, you can move it. You can always move it, right? Did you all have it scheduled? Okay, a lot of you have it scheduled. Okay, well, my goal with today is that by the end of today, you feel like you have a guaranteed 25 points on this exam. The way that the OSCP exam works, right? I think Frank and Matt have probably explained this to you all, is that there are two 25-point boxes, two 20-point boxes, and one 10-point box. The 10-point box will be easy peasy at this point, right? You know, I'm sure many of you find your trouble to be privilege escalation, right? A lot of you probably are, that's usually the biggest pain point for people just starting here. And so the 10-point box is boot to root, meaning you hack it, you're in, you're root, 10 points, just like that. I expect all of you to be able to hack every machine, or at least most of the machines, right? So that's half points on each box. And then there's two 25-point boxes. One 25-point box, 12.5 for shell, another 12.5 for root. That's generally the hardest box on the network. The other 25-point box is the buffer overflow box. And there is, until at least the end of this year, a guarantee that that buffer overflow box will be Windows, and specifically a particular type of buffer overflow in Windows. And so today what I'm going to attempt to do is I'm going to first go back and address what memory is, because I think that some of you might not go for your OSCP and might not, you know, take away from today like really buffer overflows and like the point of them. But what I want you to understand is memory vulnerabilities, and like the real issues that are caused with memory problems. From there, I'm going to spend the entire day going step by step by step, going through vulnerable application and buffer overflow and showing you this process. Unlike hacking every box, which you've done so far, which has been different, right? Buffer overflows, although the steps are long, are very methodical. It is the same thing every single time. And that's very distinct about them, right? We haven't had that with other boxes. Sure, we have our processes, right? Like, sure, let me do my scanning based off of my scans. Let me dive into this particular service. Oh, web's there. Let me spin up Nikto and Durbuster, right? We all know this stuff. But how you get onto the machine is different every single machine. With buffer overflows, we are going to have consistency. And that's what's really unique, okay? So what I want is today, step one, make sure you understand memory and memory processes. 2, we're going to talk about this thing called the stack and what buffer overflows are. And then 3, we're going to get into learning the 10-step process of doing buffer overflows every time. And we're going to do this throughout the day. Okay? Does that sound fun? Let's get going. So with that being said, let me share my slides. Okay. If at any point you have any questions or you want me to slow down or stop or anything like that, just feel free to interrupt me and say what you're going to say. Okay. All right. So let's get started. So with buffer overflows, our outline is as follows. We're going to talk about some core concepts. I think it's important that we understand memory. If you don't understand memory, then you're not going to really understand like like let's say in the future you get a job as an application security developer, which is absolutely like a valid position that you could fall into, especially if you're interested in web development at all. You want to understand what is causing these particular vulnerabilities. The next concept that we're going to have to dive into is a particular concept known as the stack. So sort of how does your operating system actually manage doing tasks, right? It's sort of like a chef in a kitchen, right? Usually there's like one, head chef, and then there's some sous chefs and whatever, but really the head chef is really the one directing, like, okay, this is what we're cooking, how do they cook so many meals at one time, right? And so that's kind of what we're going to get into when we talk about the stack. We're then going to talk about specifically these things called registers. And if you think of the chef as sort of the CPU of the computer, or sort of like the one who's in charge of operations, the registers are sort of like the tools, like his or her cooking knife, or cutting knife. And, you can see I'm clearly a chef, right? So this maybe is a bad analogy, or like a pan or something. So we'll talk about registers there. Then we're going to talk about some of the things that you're going to be up against as hackers. So what are some things that operating systems can do to prevent you from hacking? And which protections do we care about and do we not care about? We'll talk about two here, DEP and ASLR. And then finally, we'll get into buffer overflows for OSCP. So hopefully these first two sections really set up conceptually what we're going to be doing. And then we're going to get into kind of actually performing a buffer overflow for the OSCP. Okay? Any questions before I get started? All right, let's do it. So what is memory? This is always a weird thing, but I want you to go back to foundations for a second with me, right? I mean, it's like a flashback, right? Because I'm here, I was in foundations, now we're talking about foundations again. Can someone remind me, what is memory made of in a computer? What exactly is it when we talk about traffic or data or memory? What is it? What exactly is data in terms of a computer?
It's a bunch of ones and zeros.
Yeah, that's it. It's a bunch of ones and zeros. That's the entirety of memory, right? And actually, when you just take a step back and you think about that, it should give you a little chill in your spine that goes, wait a second, hold up. So that means that if those ones and zeros mean one thing, it means my computer just does this thing. And if those ones and zeros just happen to be something other than that one thing, my computer could possibly do this other thing, right? Does that make sense? That's a bad thought. That's a scary concept. And that's something that we're going to be exploiting today. Okay. Oftentimes we see these ones and zeros encoded in a notation that we're going to be seeing a lot called hexadecimal. Right? And hexadecimal is simply just ones and zeros are a pain in the butt to look at. So if we put 4 of them together, we can create 16 combinations, right? 0000 through 1111, and we can represent that with the sort of alphanumeric characters 0 through 9, A through F, right? So often we see memory represented as hexadecimal. And these are a couple just notes again about memory, just so we have these concepts as we see these things today. This should be sort of a reminder to you. What does x86 and x64 refer to? Does anyone know that?
How many bits the computer has? The
Not
processor?
how. Yes. So it refers to how many bits can a register in a processor process per unit clock cycle. Hold up. What the hell does that mean, Corey? Okay. Imagine I gave you a list of operations that I wanted you to do today. I like for some reason I gave you very annoying homework. I said solve all these first grade math problems. 4 plus 4, 3 minus 3, 7 plus 7, whatever, blah, blah. Imagine you being able to process those numbers one at a time, right? However fast it would take you to process an operation, that's 1 clock cycle. Does that make sense? So if we can process 32 bits in a single clock cycle, that means that operations are maxed out at operations that use or consume 32 bits and no more. That means that's why 32 bits is so limiting. A 32-bit integer value, for example, meaning ones and zeros that could represent an integer, can only be as high as about 2.4 billion. Okay, it's not that high of a number. And if it's unsigned, it can be a little bit larger than that, of course. But a signed integer value can go from negative 2 billion to positive 2 billion. That's not that large when you consider numbers that we want to work with today. There's more people on Earth than a 32-bit processor could like store a number. And again, this is the processor. So this is like, when we talk about x86 and x64, we're talking about a processor that can deal with 32-bit operations or a processor that can deal with 64-bit operations at one time. For your knowledge, you will only be responsible, so if you do OSCP this year, for dealing with 32-bit registers. However, you should be aware that 64-bit registers also exist and have a sort of different amount of data that they can process per unit clock cycle. The CPU in your computer, more specifically, these bits, 64 bits, 64 ones and zeros that exist in your processor, this is like the frickin' Times Square of your computer, people. Okay, this is the Times Square. This is like the highest, most expensive real estate that you can imagine, right? And from there are sort of like a bunch of helpers, right? Like, let's say I have so many math problems that I'm just gonna call in someone random. Can I see your names here? Do I see any of your names? No, I don't see any of your names. Okay, that's sad. I can't call on any of you. I see Shlomo. Okay, cool. Shlomo, I see your name. So let's say Shlomo lives, I'm making this up, in Queens or something, right? So if Shlomo lives in Queens and our most expensive real estate is in Times Square, I can start and have Shlomo help me with some of my math problems, but I have to like go all the way to Shlomo, give him some of my problems, right? Like go back to work in Times Square. And then like when I'm done, maybe like go back to Shlomo, like Shlomo can give me some problems like later on or something, or he's completed them later on and they can come back to me. And so memory gets quite complex, actually. It ends up being this sort of chain of operations where, you know, you have sort of all these helpers who help complete operations. And it looks like this. So this is actually an internal snapshot of a 2012 MacBook Pro. If you look at this, this is pretty interesting to me. This is, you know, you see those little red squares up top above all those L1s? You see that? Those like squares? Yeah, give me some head nods. That's your CPUs. This is a quad core computer that has 4 CPUs, okay? Those CPUs are connected to registers, okay? So those have a bunch of registers. So in each of those registers are 16 or 32 or 64 bits. There's sort of this real estate that exists right outside of those CPUs, the L1 cache, that basically allows that CPU to deal with really large numbers. So for example, without L1 cache, it would be impossible for a 32-bit machine to compute a number above 2 billion. And so for those of you who are thinking like, how could have we ever computed a number above 2 billion before 64-bit computers existed? This is how. They'll put part of the number aside into this L1 cache and just like do a partial operation and then bring it back in as it needs to do it. So long story short, the thing to take away from here is like, it's a big task, like running a kitchen, where like we have all these different parts of memory that go in and out to help us out. And when we talk about this memory, we're actually talking about something called volatile memory, disposable memory. I'm not talking about like your hard drive. I'm talking specifically about memory that exists in the CPU, L1, L2, and L3, as well as RAM. That's it. And the reason why I'm making that distinction is because these are the places that get filled up when your computer is running. And remember, the machine that you're hacking is running services, right? It's running processes. So all of the data from those services are loaded up as true ones and zeros in the CPU, L1, L2, L3, and RAM. That's what I want you to understand from this slide. Does that make sense? Even if sure the application is stored in the hard drive, when it is a process, when it is actually running, it is running in RAM. It is running in cache, okay? So what we need to understand is the CPU is like Ron Burgundy, okay? Anyone see Anchorman? Ron Burgundy, yeah? The CPU will do anything that it is told. Anything that's on the teleprompter, Ron Burgundy will read, right? So the CPU will do anything that it's told. So if somehow we can infiltrate this system and tell the CPU to perform some operations that it did not intend to do, it's just going to do it. There is no security that exists at this level. I want you to understand that. This is a bunch of ones and zeros that exist to simply compute operations or do math or do some very basic process. There is no security here. So we will infiltrate the security of which this memory is managed and inject our own malicious code into that memory, tricking it like Ron Burgundy to run something that we don't want it to do. And that's kind of what we're going to be doing today at a high level. Okay. So let's be a little, let's go the other direction and be a little bit more abstract now. Okay. Again, pause me if you have any questions or anything, but I want to talk now about how an application works on your computer. So an application is running on your machine, and the application needs to use memory because that's how things work. Nothing can work without memory. Is that clear? Like memory is everything, right? Like memory 100%. So this application doesn't just get to go, I will take memory over here. No. There's a boss, there's a bouncer at the bar who says how much memory you can get and where you can get the memory from, right? And that is the operating system or the kernel, right? That's who really says you can have memory, you can't have memory, or you can have memory over here. And the operating system itself, the kernel specifically, is responsible for maintaining where the memory is available and where it is not available. Okay. And again, when I'm talking about memory, I'm talking about RAM or cache. I'm not talking about hard drive. So this is not on the order of like terabytes. I mean, usually, but you know, that's what I'm saying. This is like gigs or megs. Okay. So the application says to the operating system, which has a bunch of memory, and here's a bunch of memory slots. For our simplicity, I'm going to number these slots 1 through 12. And there's some other processes that the operating system is already doing. Maybe it has some background stuff. Maybe there's other applications running. I've blocked out the application memory that's unavailable already, and that's in blue. So right now, when this application requests memory, the operating system is going to ask a couple of questions, right? It's going to say, how much memory do you need, right? Can I stick you in one of these blocks? And these blocks, for our sake, can be 1 byte of memory or 8 bits or 32 bits or 6. It doesn't matter. Some arbitrary size of memory. And so I just need 1 block of memory. Great. Doesn't matter where. The operating system goes, great. Let me get that in the next available slot for you. And so it might just stick this here in 5. If it goes ahead and it does that, right, the application later on might come back and go, I need more memory for what I'm actually trying to do. Yeah. And now there's a problem. Because of the fact that 5, right, is over here, and 6 and 7 are maintained by some other process, 5 now needs to be linked to another cell in memory. So in this case, 5 might be, you know, this application might be granted 8. This makes things a little bit more complicated because what happens is now 5 needs to sort of use some of its memory. It's like almost like an R.L. Stine novel. Anyone remember those books that's like go to page like 67 at the bottom? You know what I'm talking about? Part of the memory in 5 now needs to be used like this R.L. Stine novel where we have to point to the next place in memory. So if we're trying to create a complex application, there's sort of like, all right, start at 5, go to 8, go to 11, go to 13, back to 6. This one just came available, go to 2, right? And it becomes this complex nested structure of memory. This is one way that operating systems can define memory. And this is how you can have inter-application issues. For example, let's say the memory that's allocated for 5 is so small and the operating system doesn't do a good job at making sure that let's say the memory for 5 is 32 bits. And I just told you the largest 32-bit number, an assigned 32-bit number, is about 2.5 billion, okay? Let's say that this application tries to write 4 billion into that slot, right? If it tries to write 4 billion into that slot, depending on how good this operating system's defenses are, right? It's possible that that memory will override some of the information in either 4 or 6, depending on which way this goes, which could totally crash another application. Does that make sense? So that's one issue to note here. And that's not the kind of overflow we're going to be dealing with today, but it is a potential overflow that can happen. These are more known as heap overflows, but just so you know that these are typical overflows that can happen. Anyway, what it comes down to is the operating system has 2 choices when it allocates memory. It can allocate memory in a contiguous fashion or in a linked fashion. And these are what the 2 look like. A contiguous fashion means that we sort of block out a large chunk of data for a particular application. And this is generally the preferred way of doing things. It is a lot more performant from a computing standpoint to go, oh, all of this function or all of this program is loaded into this area in memory, instead of like following this wild goose chase to go around memory, right? Like, because you have to like read through, like sort of, this would be like if I only know one of your names, which I only do right now because the only Shlomo's name is here for some reason. So, oh, I see Michelle's name too, I guess. So let's say I only know Shlomo. And Shlomo only knows Michelle. Michelle only knows the next one and the next one, the next one. That's what linked data looks like, right? Like if I wanted to get the sixth person in this chain, I would have to like say, hey, Shlomo, who do you know about? And then Shlomo would have to be like, well, I only know about Michelle. Let me go to Michelle. And then Michelle would have to go down the chain and continue this process. You see why that's a little bit less inefficient for computers to do? So operating systems tend to want to do this contiguous thing. The trade-off with contiguous is that you set aside a lot of memory ahead of time, right? Like what if the application doesn't actually need a megabyte of memory? Well, now you've allocated a megabyte for an application and wasted it. So it's this like sort of, trade-off between, performance and space. And that's always a decision that your operating system has to make. Why are we talking about this? Well, let's talk about some of the decisions that your computer does when an application gets loaded into memory. And so again, to summarize, memory is requested by the application, but it's distributed by the operating system. If the application or process does not properly ask for the right amount of memory, it is possible that it might overflow outside of the designated area. So if the application or process doesn't ask for the right amount of memory, or the operating system doesn't do a good job defending against it, it's possible that both of these things could cause an overflow. Again, if we look at this situation right here, 5, we overwrite this block, we have an issue. Here's a really simple example of a buffer overflow in memory. This is an application where 2 variables have been defined, both an integer x and a character buffer. In lower level languages like C, instead of Python, which is, Python is sort of this beautiful language where you don't need to worry about types that much, right? You just say like X is 5 or X is cookie or X is true, right? You don't have to be like, this is a Boolean coming at you today. This is an integer. Look forward to this Python, right? And you might not feel spoiled by that, but you should. Because lower level languages have to go do the operating system and go, hey, buddy, look, I know I just talked to you, but I need another 4 bits or 32 bits for this integer. Can you hook it up, right? And so this is what happens. I'm not joking. Like this is what needs to happen. Python does all this for you, so you don't really have to think about it. But let's take a lower level language here. Each block in a lower level language, we're going to call a byte. A byte is just simply 8 bits. So when you hear about megabytes, we're talking about millions of 8 bits. The reason why we say 8 bits is because usually it's, in modern standards, it's basically impossible to do anything less than with less than 8 bits. It's very difficult to represent anything with less than 8 bits. You need 8 bits. And so we categorize 8 bits as a byte. So for this particular application, which seems pretty straightforward, it needs 4 bytes or 32 bits for an integer, as well as 10 bytes for a character buffer, AKA a string, by the way. A character buffer is just a string, what we call a string in Python, right? So, I shouldn't say that because one of you are going to be like, well, actually, technically, one is static. I don't want to hear it. You're ruining. You're missing the point. You're missing the point. Let's effectively call them the same way. So in this situation, we have int x, which is declared and defined itself needing 32 bits, and we have a character buffer, which is 10. Because of the situation that int x was like written to and buffer is over here, if we start to write into this buffer more than 10 characters, or in this case, 14 characters, because of the fact that these two things are right next to each other in memory, all of a sudden, our integer value will be read as ERS, whatever that special character is, and termination character, right? And so we override the entirety of the buffer. There's nothing stopping the writing operation, and that's what this string copy is. Now, I know this might sound silly to you, but there's really not much a memory level of a computer could do. Processes could stop it, operating systems could stop it, but once we get to the 1s and 0s, there's nothing that we can do. Does that make sense? Like this is just gonna happen. These two happen to be next to each other. We wrote into memory, it would be like, It'd be like if you were like, I don't know, bulldozing a street and I told you to start at house 1 and bulldoze until house 6 or something, right? And then like, instead of saying 6, I like wrote down like it looked like an 8 on the piece of paper that you were reading or something. So you like bulldozed houses 1 through 8, not realizing that like the 7th and 8th house were not part of the property that you were supposed to bulldoze, right? Like at that point, there's nothing that you can do. There's no logic at this level. It's just simply copy into memory. It's very, very, very simple. Okay, so this is the first buffer overflow that we're going to explore today. Okay, and this is going to be the first thing that we're going to do is we're going to play around with a vulnerable C application that does exactly this, just so we get this concept. Before I go on, are there any questions on this so far? Okay, so here's the problem with what we've done so far. We actually have already understood that we can overflow memory. But what we haven't understood is how do we trick the application into doing something that it shouldn't be doing? Because in this case, all we're going to do is create an integer that just doesn't make sense, right? Let's say this application is using this integer, right? ERS, whatever. That's not a valid 32-bit integer. Does that make sense? Like there is a character op, like a equivalent, like to ERS, whatever that termination character is. Like there is a bit equality that ERS blah, blah, blah would represent as an integer. So when this application goes to use an integer, let's say before this, the integer value 000 through 0001 or something. So like the number, the decimal value 1 was stored there. Now, whatever the decimal equivalent of ERS, that termination character is, will be the value that the application uses. Does that make sense? I know it's like a really tough thing to wrap your head around, but like this application is like now, again, Anchorman, Ron Burgundy, like when it goes to actually use this integer, it's just going to take whatever value was in X and use it just like it normally would. So if the function was add 2 numbers or something like that, where it was like, had an X and a Y, if X was previously 1 and we've overridden X, whatever the 1s and 0s equivalent is of ERS and thing, equivalent as in number, would be how the application uses it. This doesn't change the context of the application. This only changes the memory for the application. Let me explain. Maybe a CyberChef example would be really helpful here. So, like, let's say, for example, that like we have, what was it, like ERFA or something, like that got overridden into a buffer. If we like go to decimal from here, right? And then like we get our decimal value, actually we should go to binary, right? And then this is the binary. And then we want to go like decimal. Is that gonna work? Not quite. Anyway, like, let's see, can we like decimal to binary to decimal? Let's do this. Is this too long? Okay, there you go. So like that overflow, does everybody understand what I'm saying here? Like that overflow, although it screwed up what the value was supposed to be in X, so long as this X was a valid X, it might not even crash the application, right? Because like that integer X is still going to be read as an integer in the context of this application. We're not like screwing up how the application works. That's being held in a different part of memory. We're just screwing up what the variables are. Does that make sense? Like we screwed up what X was, but we didn't screw up like how X is being used. It's sort of the difference between definition and use in code. Does that make sense? I need you to get this idea because this is important, okay? Like we overflowed ERFA, which happened to be this equivalent of 1s and 0s, but when the application is going to use it in the future, well, it's not going to crash it as ERFA. It's going to still interpret it as this, but this decimal value may or may not crash the application depending on what the application is trying to do with it. I don't know. So long story short is like this itself isn't going to like let us be like hacking machine after machine after machine, right? This is cool. We can overwrite memory now. Yay. We can crash applications. Yay. But we don't have control of the application. And that's what we need. Does that make sense? So let's take it a step further. and actually understand how buffers actually write themselves into memory. You see, this is something that's existed for a long time. But basically, here's the idea. Whenever a function gets defined, okay, the function itself gets defined, the parameters of that function get defined, as well as the return address to go back to when we're done with the function. This is important because what happens, okay, let me draw this out. Let me open up like a REPL. I think this will make it a little bit clearer. I'm gonna open up Python. Okay. Actually, I'm gonna do better. Excalidraw. Excalidraw.com. Okay, so Excalidraw. Okay, so I'm going to do one better for you here. I want you to imagine this. Let's say that you have some function that it's called like add two nums, which takes an a and oops, sorry, I'm writing JavaScript. Everybody, I'm sorry. Def. You'll know def. A and b. So I'm going to define two numbers, a and b, right? And then this function is going to do something pretty simple. It's going to just simply return a plus b. Really simple function. Does that make sense? Okay, so what does the memory look like for this? Well, let's go ahead and draw it out. On the left side over here, we have like 0x00. This is like nothing. This is like the bottom of our memory address. And the top parts of our memory address look like this, 0x FF. Okay? Y'all with me so far? So what happens is when we define a function in memory, that function in memory, we're going to create what's called a base. I'm going to call it a base pointer. I wish I could write this sideways. Can I write sideways? Yeah. So here's the base pointer. Okay, and so this base pointer itself is the bottom of this particular function. It basically signifies this function's done. This function's done. The next thing we're going to do is I'm going to draw another thing, another rectangle. And this right here is going to be our function called add two nums. Also going to be added to the stack, just like this. And then we're going to create our variables. A, this is A, this is B, right? And then, and this is where it gets interesting. And the most important thing is, where did we come from? I know this is a weird thing to talk about right now, but where did we come from? So like, when this function is done executing, it needs to know where in memory, where in our much larger scope of memory did we come from? Remember, your computer is running a bunch of things at one time. So like your function is like being defined, and then like we need to know where to go when we're done with that function. Does that make sense? Like when this function is done or evaporates off the stack, when we get rid of this and this and this, right? And we reach back here, is our application done? It could be done. It could be absolutely terminated, right? But more likely than not, there's a bunch of other functions too. Like, I don't know, do other thing or something, which takes an A and B and returns like, I don't know, 5 or something. And now let's say add two nums calls do other thing, and it calls it with A and B. So now we have, and let me just so you can visually imagine this in Python. Look at this. We have a function that returns 5. And this function happens to call that function, right? You can imagine this is one function just calling another function. And so we would do all of this again onto this. But what's interesting is the actual code itself. Now, that information, that's all being loaded into memory inside of this part right here. This is known as the code buffer. I wonder what that's going to do. So all of the stuff that happens inside of this function gets loaded here into buffer. So if inside of do other thing or add two numbers, let's keep it simple for a second. I said like x is equal to 5, right? Then inside of this buffer area, there will be a certain amount of memory that's allocated, right? Which is x is equal to 5. Now, it's the problem that exists in all of these systems is sort of how this buffer works. Because of the fact that more functions might occur down here, the buffer grows in this direction, which is really stupid, people. It should, like, this is really bad. But there's literally nothing we can do about this because functions themselves are going to be layered to the left of this. So we can't like screw things up downstream because this will always happen. So the way that we should do this is maintain anything that happens inside this function should be stuck inside of this buffer. And when it isn't, that's when problems occur. See, what we're going to do now, okay, is you see this buffer? Imagine now our CPU is going along reading stuff. Our CPU is reading something at 0x, I don't know, 3131 or something. So somewhere random in memory, our CPU is sort of reading and doing its thing. It's finishing some program somewhere, okay? It looks to the stack to find any variables it needs or where it needs to go next, okay? But if for some reason, when we write to this buffer or when this buffer gets loaded into memory, if the amount of space that this buffer takes up happens to go past the buffer and lands in this area called where did we come from, we could effectively, when our application finishes this function, right? So I'm gonna delete all these squares for now. Oops. So delete. When our application finishes all these functions, if when it goes, hey, teleprompter, where do I go next in my R.L. Stine novel to go in memory to find the next thing to do? And somehow that buffer overwrote that, right? We could effectively redirect Ron Burgundy, aka our CPU, to look at anything in memory that we want. If I tell it, if I can somehow fill this with a bunch of BS, right, like doesn't matter, and the last part of it says, you know, I don't know, 0x37, when I get to where did it come from, all of a sudden, we're going to be reading the information from 0x37 because that's just what CPUs do. When it asks where did it come from, and it was just a memory address to go back to when we were done, just some home address like your house might have, right? Where do we go after, right? That will contain the data, the next thing to do. It's like a box that contains the next mystery. This is the next place we have to go to. If we can control the next place we have to go to, then let's make the next place we have to go to be where our malicious code is. Does that make sense? That's the idea. Okay, I know this was a lot. So that's how we can go from taking an overflow and making it malicious. We have to redirect the execution flow of the application. There's no magical, like, I'm gonna inject something malicious into this thing. No, we have to redirect it into somewhere that we can load something malicious into. Okay, that's how a buffer overflow is going to work for us. We're going to take advantage of the fact that we can point the application at whatever we want. And so I'm going to show you this. So I think this is pretty good. We covered the nature of this stack. I want to show you one more thing with a stack. So the term stack, the term stack comes from it doesn't come from a stack of pancakes, but it comes from the idea that one thing is layered on top of another, right? And that you must do the thing on top before you can do the things below it. If any of you have a computer science background, this is also known as last in, first out, or LIFO, meaning that, it's sort of a very disappointing truth that with pancakes, the freshest pancake, right, is like the one that I guess you get to eat first, but then like the bottom pancake, which you made the longest time ago, is like getting cold at the bottom here, you know, and it's like getting all sad. And like, that's really a disappointing nature of stacks, but like, that's worth noting that like, we have to work our way down a stack. So if I have a stack of things to do, like call mom, do dishes, work out, send email to the landlord, play with puppy, have a party, all these fun things that I want to do, right? There's basically two operations that we can do with a stack. We can basically add things to the stack. We'll call that a push operation, okay? Or I can process things off of the stack. Now that stack, by the way, any operation might contain a bunch of stuff, as we just said before. These are our variables, our buffer, our parameters, all of that fun jazz that comes with it. And so every time we add something to the stack is growing. It's growing. So when we want to operate on something, this is when we like can teach a class, right? So like now I'm teaching the class, I'm going to pop this off of the stack and actually utilize that information. So the popping operation is what actually causes the main thing in the processor to start being, or Ron Burgundy, if you will, to start doing things, to like start, you know, actually like computing tasks. Until then, it's just a bunch of ones and zeros sitting there. In fact, your CPU is made up of these things called registers. And so you should be aware of these registers' existence because these are sort of the key players in this entire operation. There are 3 registers in particular that we definitely care about, okay? There are, first of all, 8 general purpose registers, and these are x86-32. There are 8 general purpose registers, okay? There are 2 in particular. Okay, so these registers can be used to store temporary values. They can point to other locations. Often they are pointers that point to other locations in memory. This is your highest like level of real estate. Imagine this, like, look, imagine you have a piece of paper. Like this is like what a register is in terms of size. And I wanted to store like my, like, I don't know, all of my contacts of all of the people that I've ever met on this one piece of paper. I couldn't do it, right? A better tactic would be like, what if on this piece of paper instead I just like write like, look in top drawer, right? And then in my top drawer, there's like a big poster board of all the people I've met before or something like that, right? Like that would be a better way of doing this. So a lot of time these pointers, because they're so small, they're only 32 bits, are just pointers to other places in memory, like an R.L. Stine novel. Go to page 32 to read more. And then once we read page 32, it's like, oh, there's a lot of information here, right? But the go to page 32, that's really short. That's why these tend to be pointers. Okay. The naming of all of these, I don't really know where it comes from, so don't ask me, but it's all historical. But there are 3 that I want to point out to you as like sort of like the most important pointers and the ones that you need to be concerned about. Those are the ESP pointer, the stack pointer, the EBP pointer, the base pointer, less important, and most important of all. So we have the ESP. Now the ESP register is our pointer in memory that represents the top of the stack, AKA where do we go when we are done with this function? Where do we go when we are done with this function? There's the EBP pointer, which signifies that the function itself is done. It's not as important. It also signifies obviously specifically the bottom of the stack. Yes, you can have an overflow with an EBP. It just tends not to happen as much because we would have crashed the application before like we would have done that. So usually it can happen. So don't like memorize that ESP is going to be the only one, but it is certainly the most common one. So basically it is the job of ESP to be the right-hand man, all right? The right-hand person, I should say, to the EIP register. Sort of the boss, the Ron Burgundy, the anchor to this entire operation is the EIP register. Computers are stupid, and whatever is inside of the EIP register will be read by the computer. No security, no rules, no nothing. If it's in EIP, it will be read. It is the responsibility of ESP to tell EIP where to go next. Does that make sense? It's like EIP is a very, very, very busy CEO, and ESP is this fantastic secretary, right? This secretary who's going to provide all of the, okay, your next meeting is here, your next meeting is here, your next meeting is here, right? And so that is kind of what the job is of ESP. And so ESP always points to the next return address on the stack, aka the top of the stack, okay? So in other words, if we were to look at this, EIP might be working on the segment of memory that contains all of the information about calling mom. And when we're done calling mom, EIP is going to be like, what's up next, ESP? And ESP will say, it's time to do dishes, which you can find at memory address blah, 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 blah. Great. And now that will be handed off to EIP to go and do dishes. Make sense? Now that we have this process, we are ready to go. Okay? So the first thing that we're going to look at, we're going to do individually. We're going to do individually. We're going to spend a little bit of time working together through the first exercise. You're going to play around with this individually, and then we're going to put you into pairs for the actual buffer overflow section that happens today. We still have a lot more to cover. We don't have a lot more to cover in terms of concepts. Like those are all the major concepts I'm going to cover with you. Is understanding that we are going to be overflowing a buffer in the attempt to overflow the return address of that buffer. Does that make sense? Okay, good. And the return address is denoted as ESP. So what we're going to do is we're going to look at a particular vulnerable application first, and then we're going to go from there. Okay, so any questions before I get into our first demo? Okay, here's what we're going to do. I'm going to show you all a brief demo, and then we're going to take a break because I want you all to take a break. Actually, you know what? Let's do this. Here's what I'm gonna do. It's 10:50. Make sure that you're connected to your VPN. Okay. Make sure you boot up your Windows machine. You're gonna need your Windows client all day today. Okay. So I want you to take the next 10 minutes to connect to your VPN and boot up your Windows lab machine. Okay. And our desktop into that machine. Does that sound fair? Everybody know how to do that? You good to go? Okay. So at 11 o'clock, we're gonna move on to the next step. All right. Let's take a 10-minute break so you can all do that now. Okay, I'm gonna go. Okay, so you can all see my screen. We're all doing great. Back to okay. So there's if you go to your local disk C and you go to Tools, Windows Buffer Overflows, you'll see a bunch of different things here. Okay, so your homework for tonight, not today, but tonight, is going to be to do vulnerable1.poc. These. I want you to do this one. Okay, this is going to be your best test at buffer overflow. That's your homework. Okay, not now because you're not ready. We haven't gone through a single example yet, but that's going to be your homework. That's this folder. Okay, so again, local disk C, Tools, Windows Buffer Overflow. There's a file here called string copy. Okay. And so this is a string copy operation. And let me show you the code to this application. The code for this is, oh, you know what? It closed because I restarted my computer. So that's why it's not opening. One second. Okay. The code for this is over here on the left. Okay, I want everybody to look at this code. Now, you don't need to know C, I don't care, okay? But I wanna just explain it to you line by line so you get the idea, okay? The first, there's this thing called the main. I think you learned about mains in Python, yeah? The same concept. It's like sort of this main code block that calls other code blocks. In other languages, it's required. In Python, it's not. So there you go, that's what a main is. Ignore the rest of that jazz in the front part. Then you see this thing called char buff64, which basically says define in memory a thing called buff, right? That is a buffer of 64 bytes in length. So define a place in memory of 64 bytes in length. Make sense? Then this application checks to make sure that there has been an argument provided to this application at the, at command line. Think of this as like sys.argv, right? Where we like check to see that there's a certain amount of arguments. And if we did sys.argv.length, we would get the amount of arguments that are provided in Python, yeah? Or sorry, not dot length. Len of sys.argv, you would get the length of it. Y'all with me? In Python. Here, we have this thing called argc, which tells us how many arguments are getting passed in. And so basically it tells you, look, if you're not getting any arguments passed in, just return an error. So like this there's some self-defense that this application clearly thought about error handling in the first place, right? Because like they are saying like, oh, make sure the user actually provides something for this application to even run. Otherwise throw an error, right? That's what this is saying. Finally, once we've gotten past that if statement, we have this operation called string copy, which basically does, what it does is it takes the user input and strictly copies it into the argument provided in the first position. So in this case, the buffer that was defined, which is 64 bytes long, it will copy the argument in argv1 into that. So like the argument that was passed in by the user, it will be copied into memory at position buffer. Make sense? The thing to note here is that the buffer is 64 bytes long, yeah? The buffer that's been defined here is 64 bytes long, but there's nothing here checking what argv's length is. Do you see that problem? Right here, nothing is defending against the user input. We're basically saying as long as there is user input, just copy it into the buffer. And this is where this application goes wrong. If this application instead said something like if strings.if argv1's length is less than buffer.length, then string copy. No problem. Problem solved. Make sense? The issue is because we're taking user input and saying just fill this buffer with it, copy it into the buffer. And so what's going to happen here with this application, let me get out of here. So let's go ahead and navigate to this. So I'm going to open up a command terminal. Okay, and I'm just going to show you this. So I'm going to navigate to okay, so I'm going to run string copy.exe, and it's going to give me an error. It's going to say you must provide one argument. That was the code we just saw, right? I need an argument. So yeah, okay. I'm going to provide it now, AA. And this is, let me tell you people, this is the most boring application in the world because nothing happens. Like, it's great. Like, good job, Corey. Like, you did it. Great. Like, A's. Like, it doesn't do anything. There's no like feedback or prints or anything like that. That's all we did. That's all this application does is it takes stuff and it copies it in memory. But here's where it gets interesting. It's like, if I take this now and instead of providing, what is this, 1, 2, 3, 4, 5, 6 A's, I'm going to provide 7, 8, 9, 10. And I'm going to do this. Let me copy, paste. 40, 50, 60, 70, 80. We'll even go a little further, 90, 100, okay? So 100. I've copied 100 here into memory. So now I'm trying to write 100 A's into this application, into a buffer of 64. Let's see what happens. String copy has stopped working. Interesting. So something that I've done with these A's somehow crashed this application. It's hard to tell from here what happened. So we're going to be using a secondary application to allow us to examine what's happening in memory when this application runs. Does that sound fun? It sounds like the greatest day you've ever had, huh? Cool. Okay. So I'm sure there was nothing you were looking forward to after Labor Day weekend and some good old fashioned buffer overflows. So what we're going to be using is we're going to be using this amazing application called Immunity Debugger. And the idea behind Immunity Debugger is that it is an application that lets us pause time and look at what is inside of our memory at any given point in time, okay? People always ask me, Corey, why does the application have to be paused when we look at what's inside of memory? The answer is, very simply, this is happening so fast in memory that if we didn't pause, you would have no idea. Does that make sense? Like when we talk about a clock cycle for a human, we're talking on the order of seconds. When we talk about a clock cycle for a CPU process, we're talking nanoseconds. Okay, so this would be changing so quick. So let's go ahead and use Immunity Debugger. And I'm going to always run it as an administrator. And I'll tell you why. Because if there's any application that's being run as an administrator, the only way we can see it is if we are running Immunity Debugger as an administrator. So the first rule of thumb for your OSCP, so that you don't need to be worried about whether the box that you are trying to hack is running the application as root or not as root, always just run Immunity Debugger as administrator. So you don't need to worry about that, okay? That's the first thing. with Immunity Debugger, we have two options. We can open up a file to run, or we can attach it to an existing process. Because we're looking at a program that is stationary and is not running, it's not a service like a web application, we want to open, not attach. And I'm gonna now locate, right, on here, the file in Tools, Windows Buffer Overflows, and String Copy. Before I click Open, actually, you know what, first let me just click Open. When I click Open, you'll see that the application pauses and all is fine and dandy. You'll actually see that this application, right, when it loads up, it pauses it right before it starts. And you can even see, let me see if I can make this bigger. Appearance, fonts. Okay. Did that help? That made it worse. View.
Might be able to go into the options bar on the top. Forgot if it was like options or view
Oh,
or something.
yeah. Appearance or something, and then general, fonts, terminal. Let's go fonts. Let's change it. Can I? Oh, yeah, there we go. Okay, cool. I'll do Courier New like 20. Is that too big? Let's do like 18 or something. It's a lot of stuff. That felt like it did nothing. Did I just, I think I just changed what a font was. So we gotta just find that font. View, no. Appearance, fonts. Does anyone know what I just called it? View. Okay, options, appearance. Font 7. Height. Font 7. Okay, font 7. That's what we're looking for. Font 7. Appearance. Font 7. Okay, that's really big, but okay. It's better than nothing. Okay, so I'm assuming you can all see this now, right? Okay. You'll note that, like, look at this. String copy was literally loaded into memory. Isn't that pretty cool? Like, you'll see, like, this is an operation that was literally loaded into memory. So let's go through this interface really quick, okay? I know it looks like an alien interface, but don't be freaked out by it. There's 4 major things that you need to worry about. This is what Ron Burgundy is reading. Okay, this is what our EIP register is processing. So basically, there's these operations and all these things that it has to do. It's going to start working through here until eventually it reaches something that tells it to jump or go elsewhere in the particular code. And so this is EIP. You can note that this is EIP because 004014E0 is the address inside of EIP. Notice it's even separated from the other registers. That's how special it is, right? 004014E0, this is address 004014E0. So whatever this reads, this address is what is actually being read in memory, straight down, until we trigger or hit our base that tells us to leave, which would then say, where do we go next? And so the next place we're going to go to is where ESP is pointed to, right, which is 0065FF84. And if you notice, that's the top thing on our stack on the right side. This bottom right is our stack. And you'll see that 0065FF84 is where do we go? We're going to, oh, this is the only function we need to run. So we're going to return to the kernel when we're done. You see that? You don't need to understand all this code, but you just got to see that. Look, EIP is basically saying, what are we doing? And ESP is pointing to the next place that we go when we're done with this EIP stuff for now. Make sense? Y'all with me? Okay. Finally, this on the bottom we'll get here, but this allows us to kind of see what's at any particular address in hexadecimal, and we'll get to when to use this. For now, if I release this application, it will just terminate because it's done now. There's nothing else to do. We hit a return, we're out of the application, and that's it. Like there was nothing to do. Like, it was a very short application, nothing crashed, nothing went wrong. We terminated, we ran to completion. Let's do this again now. And what I'm gonna do is I'm gonna open it again. And this time I'm going to open string copy, and I'm going to provide it a bunch of A's. 3, 4, 5, 6, 7, 8, 9, 10. I'm going to click open. Okay. So I've gone ahead and I've done that. I've paused here so far. And let's see. Let's see if we go and we follow this. No, we can't. We're not going to be able to see it. Okay. Let's see if we can get to it at any point. So what I'm going to do is I'm going to step forward one step at a time. And I want to see if at any point we can see where our A's are. No, we're not going to be able to see it. Here's the string copy operation. Is there any A's? Yeah, it should be here. Yeah, so even in this case, look, we can't even see the A's because like they're not being shown on the stack because they're not even involved in the stack at this point. So I'm gonna let this run to completion. I don't think we're gonna see the A's. Yeah, okay, that's fine. That's great, that's what I wanted. So now what I wanna do is I wanna do this one more time. I'm gonna open up string copy, except this time I'm gonna provide too many A's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 20, 30, 40, 50, 60, 70, 80 A's. Y'all ready for this? Watch EIP, which was a normal register before, and ESP. Watch what happens. Okay. I load this into memory. The application hasn't started yet. I'm going to let it just run itself to completion. But note, EIP right now is pointing at this memory address, and ESP is pointing at 0065FF84. Yes? I'm going to click run. And now the application has paused, not terminated, because we haven't exited the application. The application has crashed. We know the application crashed because it paused randomly. It wouldn't have paused unless the application crashed or we had set a breakpoint for it to pause. Does that make sense? So we know something went wrong. The next big clue is take a look at this. Look at what EIP is. 41, 41, 41, 41. Anyone know what 41 is? Nobody? Does that make sense? The hex opcode of an A, the hex equivalent of A is 41. So let's try to understand what's actually happening here. Somehow in this application, we ourselves put a bunch of A's in and EIP became filled with 41, 41, 41, 41, 41. But the only way that this would have happened is if at some point we had overridden the return address by ESP to point to location 41, 41, 41, 41, because we know that ESP hands off its information to EIP. In other words, our goal with any buffer overflow is twofold. One, we want to overwrite the data inside of EIP, meaning we take control of this application. If we don't gain control of EIP, that means that we cannot exploit a buffer overflow in the way that we plan. This is the most important thing. If EIP would not have been cleanly overridden by my A's, that means that we don't have control over EIP. Remember, whatever addresses in EIP will be read by the processor. Yes? And so at this point, EIP is trying to read memory address 41, 41, 41, 41. So let's go to memory address 41, 41, 41, 41, shall we? So let's jump to, is this it? 41, 41, 41, 41. No memory on the specified address. So it looks like we're telling EIP to jump to a memory location that just simply does not exist right now. There is no opcodes there. Is this bad or is this good for a hacker?
Good.
This is great. Because now, if instead of me writing 41, 41, 41, 41, right, I instead wrote a location that contained our malicious payload and forced EIP to start reading from there, we're in. The second thing that we need is a place to put our malicious payload. And that's the second thing we need. So the first thing we need is we need to cleanly overwrite the value of EIP, giving us control of the execution of this application. The second thing that we need, okay, is that a register's data, not the register itself, the register's data. That means like the shipping label on the box is still good, but the contents in it have been switched with our malicious stuff. We want the contents to be swapped in any particular register. The most likely one, as we spent the entire morning discussing, is ESP. You'll note that ESP is still pointed to the same nonsense, 0065 FEC0, that it was before. If you go back in the video later, you'll see that. This is important because if we go to this thing in the dump on the left side, you'll note that at FEC0, right? We have a whole bunch of A's that come right up to it. In fact, let me do this one more time and show you what happens if I include 100 A's. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, yes, I want to terminate it, run it again. Okay, look, 0065 FF84, EIP is pointing at something totally normal, living a good life, having a good day. Things are great for EIP, no problems. I'm going to release the application. And now look, all of a sudden, not only has EIP been overridden, but ESP has not been overridden, but the data inside of ESP has been. Do you see that? That means that if we tell EIP to go to location 0065 FEC0, if somehow we replace these 4 A's with this, it would start running the code. Make sense? Meaning I could put my malicious code here and redirect EIP to look at ESP to run my malicious code. Okay? This is not easy. I told you it's very hard to wrap your head around, but that's the concept that we're going to be working with now. Okay. So
with the so you just changed it by between this example and the previous example, it was just an extra 20 A's. Like, how does that change the ASCII text with
Good question. So like, how come this became a bunch of A's now and before it wasn't? So before, it doesn't look like we cleanly wrote into ESP's data. Like not ESP, the data found at the address that ESP was pointing to. Do you see the distinction? So what happens is here, I know that when I have 80 A's, I had enough A's to cleanly override EIP, okay? But when I had 100 A's, I got to the point that I could cleanly override EIP and begin to write into ESP. If ESP's memory, for some reason, isn't large enough, in this case, it actually isn't large enough, and I can show you that. If ESP's memory is not large enough to contain a malicious payload, which would be about 300 to 400 bytes, then effectively we would not be able to conduct an entire buffer overflow here. We would have to do something called ROP chaining, which we're not going to get into right now. But if you don't plan on doing OSCP within the next few months, you will have to know ROP chaining, FYI. So that might be a motivator for you to want to do it sooner than later. But to answer your question, A's are being overridden into memory into the memory addresses in the stack. This is the stack, right? On the bottom right. These A's, when I reached 80, had only reached here from our buffer. They haven't overridden ESP yet, okay? And so they might be at the data of ESP, but they haven't cleanly overridden ESP. So here, in this case, at 100, we finally are getting to the point where we're filling the data at ESP, and that's why we're seeing a bunch of A's here. So here's what I'm going to tell you. Your goal is twofold, okay? One, find the amount of data that overflows EIP, and two, the amount of data that overflows the contents of another register's location, not the location itself, right? We don't want to screw with ESP's location. Like notice EBP was overridden here with 41, 41, 41, 41. That means that EBP is useless to us. Because let's say we want to tell EIP to go read the thing that's in EBP, useless, right? EBP's location is not going to be helpful for us, right? Because ESP points to a location that contains these values, I can eventually tell EIP to run, or jump to the place in memory that ESP exists, which will then run my A's. Okay. So I could continue on this and show you like now what we'd want to do is identify which of our A's are overriding EIP and which of our A's begin to override ESP, right? Like that's the next thing we'd want to do here is like figure out what we just sent 90 A's. So like which of our A's are even doing this? Like, right? We don't know. But this is our goal. And this was what tells me that there is a buffer overflow vulnerability, not necessarily exploit yet, but definitely a vulnerability, right? Because I was able to cleanly take control of the application and put my own stuff into a memory location that is accessible. Does that make sense? Those are the two things that you need to take away from this. One, I overrode and got control of the application. And two, I wrote my own stuff into memory. Okay. So I will come back to this if we need be, but I'd like for us to actually turn our attention to the main event of today, which is going to be the SyncBreeze application. Okay. So let me find my slides. Okay. So there's a couple of tactics that you should be aware of that you may or may not be responsible for. And so before we go into the SyncBreeze, I want to just finish up the slide deck here. Okay. There are two major tactics that operating systems employ. There are more, but two of them that are very well known that you need to be aware of. Okay. The first is known as DEP, and the second is known as ASLR. And they are, in my opinion, extremely simple yet brilliant, absolutely brilliant memory prevention techniques. The first, which is called DEP, is data execution prevention. I can only imagine being in the board meeting when they decided to do this, because it almost just sounds like, wait, they weren't doing this already? What if when an application asked the operating system for memory, it had to tell the operating system what that memory was for? How's that sound? Does that sound like a crazy idea? Well, that's effectively what DEP is. DEP basically says that when an application asks for memory from the operating system, the application must tell the operating system, is the memory that you're looking for, should it be memory that is running code, or is it memory that is being used for data storage? These are two different things, right? Like there's the code that's running, and then there's the place in memory that's storing the value of X or Y or some variable, right? There's no reason why the place in memory that's storing the value of X or Y or some variable should ever be executable, because it should just be able to be read, right? Like actually be used as part of an execution flow. It shouldn't be used to execute. It should never be allowed to execute. So what this allows the kernel to do is basically say, hey, if the memory addresses between blah, 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 and blah, blah, blah are ever attempted to be read by EIP, stop. Don't do that. You're not allowed to do that. These are read-only. These cannot be used as, these are not allowed to be executed. You can't execute here. You can only read from these places. You can't execute here. And so if memory has depth, if an application or any of the applications that are being used by that application, which is another topic that we're gonna have to cover, use depth, what that means is that you need to make sure that you're overriding into memory in a place that is executable. If it is data for storage or read-only, then you're out of luck. You're never gonna get EIP to execute that area, and it's just gonna crash, that's it. And you're not gonna gain control of that system, okay? I should also mention, by the way, that in real world, buffer overflows are, you'll never see these in bug bounties, right? Because a lot of the time, buffer overflows will just crash the system. There is almost never a case where like a buffer overflow, like when you're like testing a buffer overflow, like things go fine. And like, unless you fully compromise that system and keep it online, you are not going to keep that system alive, which is why on the OSCP, what you'll do is you'll practice on your own personal Windows machine 12 times, 50 times, 100 times. And then only when you're ready, you'll attack the actual machine with the exploit that you built. Does that make sense? Like once you do this, you take the service offline and you'll need to revert the machine because you don't have access to that machine. You'll have to use a revert on it. So you want to practice on your own machine. So this is the first defense mechanism. Any questions on depth? I think it's so cool because it's so simple yet so brilliant. Okay. So you are guaranteed to have an ability to sidestep depth as of right now on OSCP. That is, you will not have to worry about depth on OSCP. You will have to worry about making sure that the thing that you're using is not using depth, and we'll talk about that, but you won't have to worry about you having to sidestep depth protections or something. Like there will be a way to sidestep these protections. Do you see what I'm saying? This is not something that you have to learn to override today. You should be aware that it exists so that when you see things like depth protections, you're like, oh, I'm not gonna use this thing. I'm gonna use this that doesn't have depth enabled. The second major type here is ASLR. And this one's a little bit also pretty obvious. This says, okay, that when memory is being allocated by the operating system, the assignment of where in memory it is occurring will be different each time. So in general, when we talk about RAM, we're not actually all of what you just saw is not actual RAM. It's called VRAM or virtual RAM, meaning that, yeah, sure, an application might be running at this spot in memory or this spot in RAM or this spot in RAM or this spot in RAM, but when at that spot in RAM, it always loads to the same relative location. So if we start at location 0 in master RAM, if we don't have ASLR enabled, that means that it's always going to load this function to spot 50, let's say. If we started at 3000 in RAM, it would just load it at 3050. If we started at 6000, it would load it at 6050. Does that make sense? If ASLR is not enabled. If ASLR is enabled, okay, then a place in memory in which a function is defined or a variable is defined is always going to be different. And this is a very, 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 very difficult thing to get around as a hacker. This is really hard, right? Because now you don't have any sort of awareness of where things are being loaded in memory. You will be responsible for dealing with ASLR a little bit. You will have to deal with ASLR. You don't need to deal with depth, but we will have to deal with ASLR. If we didn't have to deal with ASLR, I could teach you buffer overflows in about 5 minutes, people, okay? But because we have to learn a little bit about ASLR, we can't, okay? And I'll show you why. So OSCP buffer overflows. You will only be responsible against a buffer overflow against a vulnerable Windows machine. You will also have a scaffold already of non-exploitable code against a particular service, okay? And you will not be responsible for truly bypassing ASLR or depth. However, you will have to be aware that ASLR will be enabled, and I'll show you the distinction there. So you don't need to bypass it, but we do have to keep in mind that ASLR is enabled. There's a difference, and I'll show you. Okay. Whew. We're ready. We're ready. We're going to do this. I know this is a lot, but we're ready to go. Okay. So here we go. Here are our steps for performing a buffer overflow. And right now, what we're going to do is we're going to get started and go through them one by one together. Step 1, run the vulnerable application and attach it to Immunity Debugger. Step 2, make sure that you have a script that can normally communicate with the target protocol. So verify that like you are able to communicate with the protocol that you're attacking. So if it's an HTTP protocol, like it's a web server, then you want to make sure that you have a Python script that can just normally send stuff at that thing, make a request, whatever it might be. The third step that you want to do is find the amount of input, okay, from our script that will cause something weird to occur in an application. So we would try, let's say like we're trying to exploit a particular, again, all of these need to be user input points, right? Like where can the user provide input? Maybe it's a search box, maybe it's a login form, whatever. In the case that we're gonna do today, we're gonna do a login form. So we're gonna perform this thing called fuzzing, which allows us to sort of use a single character like an A or a B or C, and we're gonna add more and more A's until we find out like if the application crashes. From there, we're gonna find out like which registers contain a memory address where the data has been overridden. So once we crash the application, we want to make sure that our overridden rules that we just talked about actually apply. So we need to like figure out which registers are overridden, right? Like this is only good if it's EIP. If EIP is not overridden, game over, move on. Like this is not an exploitable thing that we can do. Like we need EIP, right? Once we find EIP, we're then going to find out where do we gain control of EIP and where can we put our payload. And that's the start. Okay, these are the first 5 steps that we're going to do. There's 10 total, and this is where we're going to start. Let me also give you one more tip. Today, we're going to start with step 1 through 3. On OSCP, you will have already been given a script with a known amount to crash the application. You will not have to fuzz. Okay, unless they change something drastically, you will not have to fuzz, but you should learn how to fuzz. Okay, so we're going to do a Simon Says thing here now. Okay, so Frank, you make pairs for all of them?
I have the pairs. Let me set up the breakout rooms.
Okay, cool. I'm going to go through a demo of what you're going to be doing now. And then I want you all to repeat exactly what I do in the first step, just so you get the process. And I want you to talk to each other, ask questions, call for help, and really get it. Because even though we're going to be doing this on the Sync Breeze application, it's going to be very similar on any application that we do this on. Okay. Okay, did I mess this up? Please tell me I didn't. Okay, all right, cool. So before we get started, I'm gonna send out a snippet of code that you have been given. This is not like something that you should have come up with, but, oh, I think it's in my documents. Okay, so nanocolumns.py. Okay, yeah, this is it. So this is a script that you've been given. Okay, let's understand this script. This is a script that is going to create sockets, okay? And it's going to send a buffer of size 100 in the username field of a post request to the IP address that is provided. We are going to be performing a buffer overflow exploit against the Sync Breeze application. And so to start this up, I'm going to go to services. I'm going to scroll down, or I can just start typing probably, sync, S-Y-N-C, okay, Sync Breeze, and I'm going to click start. This will start up the Sync Breeze service. The Sync Breeze service requires root permissions and will be started as root. Therefore, to see this application, right, I would go in here to Immunity Debugger and I would need to run it as administrator. But let's understand what the Sync Breeze application is. I'm going to go back to my Kali machine and I'm going to simply, okay, go to 192.168.145.10. And you'll notice that it's a web server that I can access, like I could any web server. That is why the script that we have been given looks exactly like, if you remember, Burp Suite, right? The raw HTTP. This communication is exactly the plain thing that we have. Okay, so now we have an application that goes and does this. And the first thing I'm going to do is I'm going to copy this and send it to you all, because I want you to have this. It's in your, this is in your textbook, by the way, too. I'm not like, okay, 2008. Okay. Starting script. So this script will not crash the application, okay, but it will allow us to communicate with that machine. Okay, so the first thing I want to do, of course, is verify that I can actually communicate with that machine, which is going to be really hard to do. I don't know if there are SyncBreeze log files. There must be SyncBreeze log files, right? But let me see if I can find, like, oops, oh God, I hate when I do that. Nope. There it is. Okay. Let me minimize the whole thing. Okay. I'm not sure where they're stored on here. We can Google it, I guess. Save logs to,
Do you know if SyncBreeze is on the XAMPP control panel?
I'm sorry?
You're looking for SyncBreeze logs, right? I'm wondering if it's on the XAMPP control panel on the Windows client.
I don't know if it would be there, because I don't think it's being started by XAMPP. Yeah, it's not. Port 80 in use. Yeah, it's not. This is like trying to launch Apache Tomcat, I think. That's sad. Let me search this PC for SyncBreeze. So let's understand this. So right now what we want to do is we want to take our script and make sure that it's actually working. It's kind of hard to do this without, another thing we could do, right, is we can also just monitor network traffic, right? We can set up like, let's see, SyncBreeze config. Okay. I don't want to hold this up for this. I'll find these logs. For now, this works, and I'll show you that it works. So we have SyncBreeze here, right? We could do stuff here if we wanted. Try to log in. It's going to tell us no. Feels like a normal application. Like nothing's wrong with this. Turns out there's a buffer overflow in the username portion of this form. Everybody understand that? There is a buffer overflow here. Now, how somebody would have found this is they would have tried like every possible user input in an application with like enormous inputs, seeing if they could crash the application. What we want to do right now is we want to find the minimum amount of characters that it will take to crash this application. So right now, what we'll see with 100 is if I try to chmod plus x comms.py and I attach immunity debugger. So immunity debugger is running. I'm going to attach this to the SyncBreeze application. Here it is. SyncBreeze just got paused. I'm going to release the SyncBreeze application. Now it's running. Okay, you can see that it's running on the bottom right. What I want to do is I can send this communication /comms, which takes in an IP address 192.168. 145.10. That's the Windows box, right? I'm going to send it. It sent the evil buffer, done. You'll note that it doesn't crash the application because, well, we didn't overflow anything. Everything was just like, it was like a normal login attempt that failed. Does that make sense? So what we want to do now is we want to find the amount of the amount of payload that we need to crash this application. It's also worth noting that there is a possibility that an input is too large where it will uncrash the application. And I know that sounds weird, but it has to do with the way that the code is processed, compiled, and written. So if the input size is so large, there might be other conditions that protect the memory. You might be writing to a different place in memory that changes where EIP is looking at and starts a different thread. So you need to actually be really careful with this. So you want to always find the minimum payload that we can put to crash the application. And so what you should do is you need to try to find the minimum that we need by increasing this size. It doesn't need to necessarily be the minimum, but a reliable amount. So, try this with 100, try this with 300, 400, 700, whatever it might be, and increase the size of our input until we crash the application. I want you to write a script that might try to do this for you, okay? And this is going to be a fuzzing script. So I want you to write a script that's going to basically do this for us. So, maybe I have size is 100 and I wanna, do something like, while my size is, less than 10,000 or something, 1,000, yeah, 10,000, right? While this is happening, then go ahead and do this. Oh God, I gotta indent everything. Yeah. So yeah, I could do something, and then at the end, of course, I'll do, size plus equals, 300. Move up by 300 at a time or something. You see what I'm saying? So like find your own way of fuzzing this and find at what point will the application crash. Okay? Does that sound like a fair first exercise? It's 12 o'clock. Frank, let's put them into their pairs so you guys can pair program on this. Just get the fuzzing working. And when we're done with that, we're going to know the amount that we need to plug in here for size to actually crash this application. Okay?
All right, then open the breakout rooms now.
Thanks. You have 30 minutes for this. Continue recording, and let's get right back into it. So, what?
Oh, I saw record pause. Okay,
And I restarted the cloud recording now.
awesome. Thank you.
Okay, I'm going to keep going. So I have this fuzzer running. I'm going to click enter, and look at this: 100, no problem; 400, no problem; 700, no problem; 1,000. It looks like things are not going well. Let's go check our immunity. And you'll note that it actually crashed our application with an input size of 1,000. Do you all see that? If your number is not 1,000, that's okay. I happen to find 1,000. And so what I'll note about this is that EIP was cleanly overridden. And the data inside of ESP, right? If you right click and follow it in the dump. Look at this down here. You'll see a whole bunch of A's. So right now, we have identified that there is a buffer overflow vulnerability in this application because we were able to fuzz, gain control of EIP, and overflow data from our A's into another register's data, ESP. Are there any questions on that? Remember that EIP controls the execution flow of our program. So the next thing that we need to do here is we need to identify out of the 1,000 A's that I sent this file, which of the 1,000 A's represent the 4 A's, which 4 A's represent the 4 A's for EIP. Do you see the challenge here? There are two primary methods of doing this. The first one is known as a divide and conquer algorithm. So what I could do is I could basically send 500 A's and 500 B's. And if at that point I saw that there were 4 A's inside of EIP, I would know that it's within the first 500 characters, right? And then I would divide that section again in half with A and D, let's say, right? Or A and C. And I would continue to do this until I find the 4 characters. There's also another really good way of doing this that works pretty well on like relatively short buffers. And it's the primary way that you will be doing this, which is going to be using sort of creating a unique pattern that is of the length of the buffer. Let me be very clear to you all. This is rule number 1. You all paying attention? You are to never, once you identify the length of the buffer that works, do not ever, ever accidentally change the length of the buffer. The length of the buffer that we know that will crash this application reliably is 1000. Unless you are by itself testing if you can use a larger buffer, do not change the size of the buffer. Everything that we do, we are going to maintain 1000 as the total size, unless we are experimenting with a larger size. I'm serious. Keep that in mind because we're going to be doing a lot of steps right now, okay? And it's important that during these steps, you recognize that if you change the size of the buffer, if, you know, in the case of SyncBreeze, it's actually not that big of a deal and the application will work fine. It's a very large range with SyncBreeze. You could get an application where 1000 would crash it and 1010 won't. And that extra 10 characters, all of a sudden you're like 7 steps in and you've added characters without like maintaining the size of the buffer. And you know, you're at a loss because now it's not crashing the application. And this happens all the freaking time. You can ask your fellows, you can ask like anyone who's taken this thing before, like this is a very, very, very common place where people go wrong. So never accidentally change the size of this buffer, okay? So now that we know it's 1000, what I'm gonna do is I'm actually gonna go back to my original one. All right, comms, and I'm gonna copy comms, and I'm gonna call this my proof of concept.py. And I'm gonna nano my proof of concept, and I'm going to change the size to be 1000. Questions so far? I saw something pop up in the chat, so I'm gonna get there. Okay, cool. So now we want to identify which of the 4 A's of our 1000 A's are in EIP and where do our A's start to overflow into the data within ESP. To do this, I'm going to create a unique string of 1000 characters. This would actually be kind of hard to do myself. I could write an algorithm to do it, but there is a good library that actually is built in called MSF pattern create. And if you provide it a length of the size you wish to use, like 1000, and click enter, it will actually generate that payload for you. Questions on that so far?
Increase the size of your screen just a little bit.
Yes. Oh, I'm so sorry. Good call. Let me clear and do this again even. So MSF pattern create, I provide a length of 1000, and look at this. I get a unique string of 1000 characters. I'm going to copy this. Okay. And now I'm going to nano my proof of concept.py, and I'm going to change things up a little bit. I'm going to say like temp buff is equal to this string of 1000 characters. And I'm going to replace my input buffer, right? So I can, if I really want to be safe, I can comment this out, right? And I can set my input buffer to be my temp buff. Everybody understand? It's still 1000 in length. All I'm doing is replacing the A's with this unique sequence that was generated by MSF pattern create. Cool. I'm going to save my application. I'm going to make sure that this is running. It's not, it's crashed. So I need to restart this, go back, stop, start, open Immunity Debugger. Yes. File, attach, SyncBreeze, attach, release. Program is running. Now, I'm going to fire my proof of concept. Again, I'm going to need to chmod this thing. Actually, I copied it, so it should be already chmodded, but okay. I'm going to run this on 192.168.145.10. Is that right? Can't see. That's 10. Yeah. Okay. Cool. And let's run it. Run it. And we go back. The application crashed. You can see that ESP was cleanly overridden. You can see that EIP was overridden. But what the heck is 42306.142? Guesses?
An address it's pointing to?
Right, but remember before it was 41, 41, 41, 41 after the crash, right? What is this probably?
It's going to be a hex that equates to some type of ASCII text.
That's right. So we have, remember, our function generated this random string. And somewhere in this random string is the ASCII equivalent of this. Does that make sense? So we're going to try to find where in this string those characters are. So I'm going to copy this, and I'm going to use the sister library to MSF pattern create. This pattern is called MSF pattern offset. MSF pattern offset. And in this case, I'm going to use the -q for query option and provide it the opcode. Or not. Hold on. There it is. I'm going to place that opcode. So it's so smart that it will actually be able to convert this back for me. Pretty cool. I'm then going to click enter. And we'll see that we have an exact match at position 780. We have an exact match at position 780. So what does this tell us? This tells us that the first 779 characters are effectively filler or garbage, right? They're sort of padding to make everything work. Then characters 780 through 784, right? Or 781, 2, 3, so 0, 3, right? Those next 4 characters are particularly important because those are where our EIP gets overridden. But we still don't know where ESP gets overridden, right? So we don't know where our data starts to fill ESP. So we might want to check that as well. There's 2 ways you can do this. One is I could actually, and this is the harder way, is I'll actually right click here and just follow this into the dump. And I'll see that I have 2BA3. Do you see that? 2 capital B lowercase a3. Everybody remember that. So the first characters that are stored within this are 2BA3. So I can do the same thing with 2BA3, and that's at 788. You see that? That tells us that there will be 4 characters from 780 to 784, and then from 788 onward, where we have this. So there's a space of 4 characters between EIP, right, and the data inside of ESP. And so what we're going to do now is we're going to rewrite our buffer to take all of these little things into account. And I'm going to show you that now. So I'm going to go back to my nano of proof of concept. We don't need this anymore. I'm going to go back to my input buffer. And I like to be very, 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 very clear in what I do. I'm going to be overly verbose in defining variables. Okay. I'm going to call this start padding, which is equal to A times 780. So I'm going to start with 780 A's, right? Because that's what we just found out. Remember, I just showed you all that? We just found out that position 1 through 780 don't matter. Just fill them with some A's. I'm then going to create another variable for EIP so that later on, when we want to gain control of EIP, we have it. And I'm going to put 4 B's inside of EIP. Questions on that? I'm then going to define filler. This is the area between the end of EIP and the beginning of data in ESP. Right? This is the data in ESP. Data in ESP is going to be C, right? Or sorry, D rather. So my filler is just going to be C times 4. How do I know this? Because if you look back at my description, oops, if you remember what I did outside of this, I found the pattern match for where EIP was. That was here. I found where the data in ESP began. That was here. And we'll note that the difference between them is only 4. So I'm filling it with 4 C's in the middle there. So I have 780 A's followed by 4 B's, followed by 4 C's, which act as filler, followed by the rest, which would be D's. So in this case, I need my D's to be the size, which is 1,000, minus the length of the start padding, minus the length of EIP, minus the length of filler, minus, and that's it. Right? Okay. And I'm going to do start padding plus EIP plus filler plus data in ESP. Okay. So if this works right, when I rerun this, because we're going to rerun this, we're going to check, right? If this works right, somebody tell me, what should I see inside of EIP in immunity?
4 B's.
Good. What should I see inside of ESP? The address in ESP should not be affected, right? But what should I find at that address?
D's.
A bunch of D's, right? And that's why I have this filler. If I don't do this, I'm going to have 4. If you don't do this, by the way, you can if this is confusing to you, the filler part, you don't need to worry about it. Just later when I talk to you about NOP sleds, make sure you have a longer NOP sled because this could be a problem. But it is worth noting that there is a filler here of 4. It's also, by the way, possible there's a filler of 0, a filler of 8, a filler of 16. So you should note that there is a filler. Okay. And I think this is it. So notice also my input buffer still maintains a length of 1,000. And let's save. Let's do this again. Of course, I need to restart the application. Right? Stop, sync, freeze, start, sync, freeze. Start this up. File, attach, sync, freeze. Run it. Okay, go back and release. Sending the evil buffer. The application crashed. Take a look. 42, 42, 42, 42. What is that? That's right. It's my 4 B's, right? And take a look at ESP. Let's go to this, follow this in the dump. A bunch of D's. And check this out. If I go up once, look what's right above it. My filler, C's, right? We just missed the, look at that. Pretty cool, right? So we perfectly figured this out now. And now we have this beautiful scaffold, right, of EIP, right, where we control it. That's our 4 B's, okay? We then have this ability to put stuff into ESP, which is 4 D's, okay? Cool. So, what are we going to be doing from here? The next step is I want you to replicate this yourselves, right? With, maybe we'll do this either over lunch, and we'll give you a little time after too. So we'll start you doing this now. But I want to just show you where this is going. Okay, I want you to understand this. Right now, we have EIP under our control, meaning we control the application flow. Does everybody understand that? We control the application flow because we control EIP. I could tell EIP instead of 42, 42, 42, 42, point at 00CA35D0, and it would just run whatever the hell is in there, right? The problem is that SyncBreeze has ASLR enabled. And we know this because if you look at where ESP crashes every time, it crashes to a slightly different location each time. I think SyncBreeze has ASLR enabled. If it doesn't have ASLR enabled, I can literally put this address right in here and just tell EIP to start reading whatever's in ESP and then replace what's in ESP, right, with a malicious shell. Make sense? So our goal is to put something malicious into ESP's contents and redirect EIP to look at the contents in ESP. So point at ESP. That's our next major goal. The other problem that we have right now, and I want you to note this, and you wouldn't know this yet, the average reverse shell payload, right, unstaged, okay, the average reverse shell payload is going to take us at minimum 300 to 500 bytes of space. And right now, we've only left enough Ds for about 200 bytes of space, right? Because we have, if you take a look at our code again, right? Let's go back. We've used up 780 for padding, 4 for EIP, 4 for this filler, and only about 200 or so remains. So what we're going to have to do is look to increase the size of our program and make sure that it still works. And so I'm going to attempt to do that now. And that's going to be the last thing. Notice that I didn't do this at the same time as the last step. I am going to explicitly go out of my way to test if I can create a larger input size. That's very, very, very different than accidentally doing it. Because now we're testing only one variable at a time. Now that we know that this will crash, if I increase this to 1200 and leave everything else the same, my data in ESP should automatically account for this because I'm using size, right? And actually, we can even try to make it even a little bit more comfortable. Let's give ourselves 1300. Let's see if we can do that. I'm going to X, save, right? I'm going to restart this application one more time. Run as administrator. File attach, SyncBreeze, release. Okay. And let's see if this does it. I sent an evil buffer. The application crashed. My Ds are here. And now, look how many Ds we've fit here now. Look at this. I can keep scrolling. All right. This is, look at this. Look at all these Ds. Crazy. So now we definitely have enough room, it looks like, for our payload. Interesting. Yeah, it looks like we have definitely enough room here, at least now, at least in these Ds. It looks like we have more area here. So we're almost at lunchtime, but I want you and your partner to start trying to implement what we did here. There's two major things we did. One was we wanted to find, once we found the crashing lanes, we wanted to find the location of EIP and the location at which we start to overflow ESP. To accomplish this, we use the MSF pattern create library along with its sister library, MSF pattern offset. We then replaced all of our random pattern with A's, B's, C's, and D's, some standard characters. We then realized that the amount of room that we had where our D's were too little. So we needed to expand the amount of size, because if we couldn't do that, we'd have to figure out another way to do this, which is still possible. And is what you have to do for the second proof of concept question that they give. But anyway, MSF pattern create and MSF pattern offset. So that's the next steps that I want you to do. I want you to go and do this yourself. I want you to find with your own length. If you found a different size to work, use MSF pattern create -L on that size, whatever you have to do, okay? And then when you're done, what we should be at is a proof of concept very similar to where I'm at right now. I'm also going to send out the proof of concept for after the step. So if you can't get to the step, you can always join us in the next step as well. All right. So here's what we're going to do. We're going to put you on lunch. I guess when we come back, we'll give you another 20 minutes or so to actually do this, maybe 30 minutes. And so we'll pick up at 3 p.m. Frank, Matt, is there any reason why we couldn't put them in the pairs over lunch, or we want to just keep them in the group for lunch and we'll put them in pairs after?
I don't know what do you mean, any reason? The only thing is today there is during lunchtime they have, oh gosh, why do I always brain fart this?
Meditation.
There it is.
Okay, so let's just leave it as is then for now.